Okay, thanks very much. So I'd like to thank the organizers for the invitation, the honor to speak here. So I never had the privilege of taking any classes from Tate. I did get to meet him a few times over the years at the Arizona Winter School, some other places, and also was always very grateful to get his illuminating responses to the occasional emails I sent to him in the early years of my career, and I'll work that into some stories later in the talk. So I want to begin, so the talk's going to consist of three parts. One on Tate's brilliant renormalization of classical Weierstrass elliptic functions, and then how that led into his development of non-archimedean geometry. And then the last part will discuss an alternative technique for analyzing these non-Archimedean spaces using formal geometry, and a variety of interesting examples that arise in that way, in one way or another growing out of the study of the Tate curve in its different forms. So we'll begin by discussing this Tate renormalization. So, of course, in the beginning, when Weierstrass and others studied elliptic functions, they took a complex torus, C mod lambda, and it was embedded into the projective plane using this orange function here, the p function and its derivative. Here's this usual expression for the Weierstrass p function. And this gives an isomorphism of the complex torus onto this specific cubic curve that has certain coefficients that depend on lambda and are given by these classical formulas. And of course, if we change the lattice by scaling by a suitable non-zero number, then we can arrange that 1 is part of a z basis, so we can write the lattice in this form for some non-real complex number tau. And in particular, the lattice is, of course, unaffected. If we replace tau with tau plus 1, we still get the same lattice. So this quotient classically was thought of as modding out by the entire lattice at once, but taking a clue from what Tate's going to do, we could first quotient by the period 1 and then quotient by the period tau, the point being that this first step, C mod z, can be identified with C star using the number theorist's normalization of the exponential function. And in particular, this p function entering into the previous slide, its dependence on tau is, of course, 1 periodic, and its dependence on z is also 1 periodic, since the p function itself is periodic under the entire lattice. And so therefore, we can write this, instead of as a function of tau and z, we can write it as a function of q and w, which will be the e to the 2 pi I tau and e to the 2 pi I z. And so we'll write it in this way as a function of w and q, holomorphic in w, meromorphic in q. Now, passing to C star kills off the first period, and the second period, under this exponential map, gets carried to q to the z, and so therefore this elliptic curve, written in additive form, takes on this multiplicative form. And the last little adjustment, the tau that we initially had, we're certainly allowed to negate it without changing the lattice, so we can arrange that the real part is positive, so this number q, e to the 2 pi I tau, sits in this range. In other words, q sits in the punctured open unit disk. Now, those coefficients for the Weierstrass cubic, they also depend only on the lattice, and therefore they're 1 periodic, and these have classical expressions in terms of e to the 2 pi I tau. In Tate's own notes on this from 1959, he gives a reference to Hurwitz and Courant. So here are these expressions, so they're a little bit ugly, but the key point is you have some coefficient here, powers of 2 pi I, and then these series beginning with 1, and then these expressions which involve this series, which is some integer power series with vanishing constant terms. So these things will come up in a few places a little bit later. Okay, so this is the basic setup of classical elliptic Weierstrass functions. And in particular, each of these divided by the appropriate power of 2 pi I is a power series with rational coefficients. Okay, so now we come back to our cubic. We remember that each of these divided by the appropriate power of 2 pi I requires rational coefficients. And so if we look at the degrees of everything and we divide through by 2 pi I to the 6th, we can absorb this appropriately into y as a cube and x as a square and into these terms so that the whole thing becomes more cleanly normalized. And so let's look at what happens, or as Tate did it. So if we take the x part divided by this 2 pi I, then there's some classical identities which wind up spitting out this. And this is the part that we're going to focus on. and so we're going to call this capital X. So this is going to be Tate's renormalized Weierstrass P function. It has the nice feature that when you expand it out in Q and W, it's an integer power series in both variables. On the other hand, the y part, which is the z derivative, well, z can be written in terms of w at the derivative level using this relation. And so then we can likewise calculate this by simply taking the 2 pi I cubed, pulling out one factor, leaving ourselves with the thing that we've already calculated, and then we transform it into w, and then we compute, and we do a last maneuver. This part is most of this. We subtract and add, so we get the x plus twice something else left over, and it happens to be this. Okay, so after the dust settles, the point is that we have Tate's renormalized Weierstrass P function and its derivative, capital X and capital Y, in terms of these new parameters W and Q, and the key point is that these things have these very nice series expansions that only involve integer coefficients. So I've just written them up here again. And I just want to emphasize that these are kind of mild additive and multiplicative readjustments of the usual elliptic functions. And so then Tate, using this, arrived at the following elegant reformulation of the Weierstrass cubic itself. It takes on this nice form in terms of capital X and capital Y, where this is not the short Weierstrass form that we saw earlier today. Apologies, but we'll see this is very useful for what comes later. And the coefficients here are these other particular series, which themselves wind up being integer coefficients with vanishing constant term. And so this thing for a given Q we'll refer to as the Tate curve, maybe call it A Tate, anyway, the Tate curve attached to the value Q. And then one can calculate, of course, as Tate knew well, this has a particular discriminant, which is the classical discriminant function. Again, everything is integral. And its J invariant is also an integer series as well. So when you write everything in terms of capital X and capital Y, everything gets cleaned up in this really nice way. Fantastic. Okay, so now let's come back to capital X. Now this series involves all integers n. And what we want to do is actually rewrite it in a way that gets rid of the negative exponents. Now, in Tate's original 1959 document, which was finally published in 1995, but led to his later work that we'll discuss, he had to analyze this to figure out the convergence behavior in the non-archimedean setting. For us, this rewritten form that we're about to do is going to be useful in a completely different way, as we'll see. In any event, the point is he takes this is t over 1 minus t squared, where t is this value, and you can also write it just as well in terms of t inverse. And so if we do that for the things that have negative exponent, then we get this modified expression of this blue part here in this way. And then we're going to pull out the 0 terms at the start, put those in red, and then you have these things. Okay? So this is the rewritten expression ignoring this piece at the end. And now we have W, QW inverse, and otherwise the powers of Q that show up are all positive integers over here. You can do something similar for capital Y, except this quadratic thing gets replaced with this little cubic identity. And if you do that, Y, again with a little piece modified just like here, becomes this. Okay? So we have these two new expressions which have the advantage that the powers of Q that are showing up only involve non-negative exponents. And I just want to highlight these polar terms here. These will come up a little bit later. And again, this is just recapitulating what I've said here, that these are now series in Q with polynomial coefficients when you expand out the geometric series denominators, and they have bounded polar parts given here in red. Okay, so here I've just rewritten them again, the x and the y, in this form with these little adjustments. And so I just want to emphasize, as I said before, that you have these contributions of QW inverse. And so what we can do is regard that as an independent variable v subject to this relation, and then we want to make that substitution. Okay? So, so now we have these interesting series expansions which have mild polar parts, but interestingly, when written in this form, the modified x and y also makes sense when w or v are equal to 0. Okay? So this will be very useful for us later when we come back to something called the Raynaud approach to the Tate curve. In any event, so this is just to say that Tate's renormalization can also be put in a form where you don't have any explicit Q inverses. And so as I said, he actually did these kinds of calculations for his purpose to see that his renormalized functions adapted well to non-Archimedean fields in place of the complex numbers. So we'll see that a little bit later. But I just want to emphasize that the form that I've rewritten things here, subject to this relation, even makes sense mod powers of q. Okay? Now, these infinite series, once you mod out by a power of q, these become finite sums, and so then these become more purely algebraic gadgets, and we'll see that these will kind of come back at towards the end of the talk in a very useful way. Okay? So anyway, so this is Tate's renormalization, and this is going to help us to connect the concrete approach to the Tate curve to a later approach by Raynaud, which was influential in a variety of other ways. Okay, so that was the story of the kind of renormalized Tate curve, and then the question is, so why did Tate do this, and what did he try to do once he made this very interesting discovery that you could clean up classical Weierstrass theory and make everything into elegant power series which have integer coefficients and not even any negative exponents? Okay, so to set the stage, we're going to fix a field complete for a non-trivial, non-Archimedean absolute value. They could be discretely valued guys, or maybe something like the completed algebraic closure of QP, something not discretely valued. And in such a situation, if you pick a point in the punctured unit disk, then we can talk about the Tate curve, by which we mean the cubic curve in the projective plane with this affine equation. And this is an elliptic curve, and more importantly, when we take its reduction, mod the maximal ideal of the valuation ring, these guys, remember, as series in Q, had no constant term, so they disappear. When you take the reduction, it becomes this orange equation, and this factors as y times x plus y, just linearly independent factors, and so this has split nodal reduction. And so Tate's theorem was that if you modify the classical Weierstrass recipe using capital X and capital Y, then your parameter W, which replaces the classical complex number Z, this recipe actually gives a homomorphism from the multiplicative group of the non-Archimedean field to the rational points of the elliptic curve, and it's invariant under Q naught to the Z. This is exactly an analogy with Tate's complex renormalization as C star mod Q to the Z in the complex setting that we saw before. And in particular, he was able to show that this gave an exact description of all the rational points by means of this renormalization. And in fact, Tate proved conversely that if you started with an elliptic curve that has split multiplicative reduction, then in fact it has this form for a unique Q naught in the punctured unit disk. Now, the document that he wrote in which he worked this all out in 1959 uses some rather tedious algebraic calculations. That's because at that time he had nothing else to rely upon. If you're able to invoke, fast forward to the future, rigid analytic geometry that came later from his work and others, then in fact the proof of this identification can be done without a lot of this algebra. Okay, in any event, so Tate asked Grothendieck in 1959 whether his calculations and his proof of this could be interpreted and give this map some kind of better meaning in terms of some global K-analytic theory. So Grothendieck initially was very dismissive about all this, and so he wrote in a letter to Serre that, so Tate has asked him about whether this could have any meaning, and then he basically says, it makes no sense at all. Why would you ever think that these horrible calculations would suggest something like that? I remain very skeptical. They're just brute formulas, some isomorphism, and maybe you could find some other equally explicit mess, and why would that be any worse? Okay, we'll come back to this. All right, that was 1959. So 2 years later, in late spring, early summer of 1961, Christian Huzel gave 4 lectures in the seminar Cartan, and he studied, motivated by the theory of complex analytic spaces, which are like complex manifolds with singularities. So he studied the idea of a K-analytic space, where K is a non-Archimedean field, but his approach was maybe from the modern point of view, naive. He was considering spaces, all points of which are rational, and he also studied the local rings of analytic functions. That fall, Tate began and largely did his work on rigid analytic geometry, and for these spaces, as we'll discuss, they incorporate non-rational points somewhat in the same way that varieties over a general field have closed points that have non-rational residue field. This work, in some sense, subsumed what was done here. We'll have more to say about that. But the work that Tate did in the early 60s on this topic, as we'll discuss, it only wound up getting published in 1971, but the actual manuscript he wrote circulated informally among various people and had a lot of influential effect, a lot of influence, as we'll see. But this issue about Tate's mathematical contributions not always being seen in published form right away, so it reminds me of the following story that I was told by Ort. So in the late 50s, Tate was here, and he got a job offer from Princeton. And Zariski was the chair of the math department at the time, and this was a Friday. And he wanted to be able to go to the dean on Monday morning to convince the dean that he had to make the appropriate counteroffer. But he recognized the problem was that, again, Tate had done all this very influential stuff, but it wasn't necessarily reflected in the published record. So he took several postdocs to the math library, and he told them that they had to go through all the math journals and of the recent articles from the last 10 years and find all the articles that acknowledge Tate and refer to ideas of his and provide him with something that he could then take to the dean. So he locked them in the library, and then on Monday morning, he had what he needed, and of course, the rest is history. Okay. Maybe he didn't really lock them in the library, but anyway, you get the idea. No internet in those days. Okay. Now, interestingly, despite Grothendieck's initial extreme pessimism, within a couple of years, he was, of course, suddenly extremely very supportive of the whole thing, and then started telling Serre during a visit to Harvard that, okay, now Tate has, begun to develop this stuff, and oh my God, there are all these great things we're going to do. I'm going to have to rework the theory of formal schemes, and then we're going to have to unify it, we'll do all this stuff. All right, fantastic. So this had one interesting consequence. So I once asked Tate, were there any reasons behind why it took so long to get around to publishing his work on this material? And he said that, well, one source of difficulties was that, Grothendieck was making so many suggestions and was so excited about the whole thing, and then after a while, there was so much back and forth between them that Tate kind of lost track of who deserved credit for what. And this kind of would be a difficulty if you try to write the paper and decide, to whom to give credit for things. And so it was maybe simpler to avoid the issue by simply not publishing. Okay, anyway, that's what he told me. Okay, so so what did he do in making this global theory? If you start over a general field, then a classical algebraic variety in the sense of Serre from the 1950s, you would take the max spec of some F algebra of finite type, finitely many variables, finitely many relations. So in Tate's approach to non-archimedean geometry, he kind of models it on this idea. He takes rings that are of the following form. So a certain ring T, well, he didn't call it Tn, of course. So what we now call the Tate algebra that I'll describe in a moment, this is going to replace the role of the polynomial ring, but we're still going to work with the max spec. So the Tate algebra is their power series which have coefficients that go to 0 as the total degree goes to infinity. In other words, these are the power series converging on the closed unit polydisk over the field. And this max spec of this ring with these relations should be regarded, loosely speaking, as being like the locus where the f's all vanish inside that unit polydisk. And this Tate algebra that replaces the polynomial ring, it has a natural Banach algebra structure via taking the max of the absolute values of the coefficients. This is meaningful since these guys are going to 0. And this does turn out to actually be the sup norm in an appropriate sense on the polydisk. Tate actually, in the early 60s, he proved some nice algebraic features of this ring and of its quotients, similar to what you know from algebraic geometry, such as these rings are Noetherian. Their residue fields at all maximal ideals have finite degree over K. There's a version of the Nullstellensatz and a variety of other things. And this Banach structure also has some very nice properties. All ideals are closed, but remember, this topology is not defined by commutative algebra, right? It's defined by a norm. All ideals are closed, maps are continuous, modules have natural Banach structure. Anyway, he was able to do a lot with this. But again, he interacted tremendously with Grothendieck, who suggested many ideas, and they both developed this quite well. Now, coming back to Husserl. So I mentioned before he gave these 4 Cartan seminar talks on the more naive K-analytic spaces. In the first of those talks, he actually showed, by adapting methods of Oka from the complex numbers, that the sheaf of K-analytic functions on k to the n has the appropriate notion of coherence in the sense of Serre, and that it stalks from Noetherian rings. The problem is this is completely useless. And the reason this is kind of not useful is because the underlying spaces on which you're working are totally disconnected, so there's no good notion of unique analytic continuation, so you can't really do much with it. So more specifically, no matter what point you pick in any open set around it, there are always going to be plenty of non-zero functions which have vanishing stalk at the point simply by using a separation. Like the origin, take the closed disk, you break it into 2 pieces. This characteristic function vanishes the origin, but it's not identically 0. And yet you'd like to hope this is somehow connected, but of course it's not connected in the naive sense. So Tate kind of very boldly decided to get rid of this problem by defining it out of existence. He simply declared that you're only going to allow the covers of this to be certain finite coverings, namely you take certain open sets roughly defined by non-strict inequalities of this type, so that doesn't allow something like this, and you simply demand that I will only consider finite covers subject to conditions like this. So in some sense, it's almost like you turn the Heine-Borel theorem on the real line into a definition, which feels like, it's kind of cheating, okay? But amazingly, he was able to actually prove real theorems based on this kind of brute definition. And this is not a usual kind of topology, so it's a somewhat subtle Grothendieck topology, but it turns out in the end to basically get rid of the separations that arise from total disconnectedness. Now, one side comment is that Tate's approach began with domains of this type, and originally this Grothendieck topology was very difficult to describe. Later work by Gerritsen and Grauert introduced the good notion of what's called a rational domain, simultaneous condition like this, where these have no common 0. And this turns out to be a better starting point, and these are used extensively in the later approaches to non-archimedean geometry by Raynaud, Berkovich, and Huber that we'll come to a little bit later. Okay, so in Tate's approach, for these domains that he's considering, he needs to attach a coordinate ring like in algebraic geometry. And so, for example, to this domain, he wants to attach something like this, where this variable is like being forced to have absolute value less than or equal to 1 everywhere. So that's how this relation somehow encodes this property. In any event, the ring attached to each domain is some kind of Banach-completed localization of the original coordinate ring A. And subject to this kind of construction, he's able to show that what's called Tate acyclicity, so this is like the fundamental theorem that gets the theory off the ground, that given any module, if you assign to each of these domains the module tensor one of these Banach completions, then this is a sheaf for the funny Grothendieck topology, and the higher cohomology vanishes. And in some ways, what's almost more important than the result itself is the method of proof, because later there were other approaches to non-archimedean geometry that were introduced by Berkovich and then Huber, and then refining Huber's approach, Scholze, with perfectoid spaces. And the technique that Tate introduced to prove this result is much more complicated than the analog in algebraic geometry, but the method he introduced is adapted very well to handle the analogous result in these kinds of situations. Okay, having built the local model spaces, the global spaces are simply going to be gluings of these subject to the kind of topology you have. So for example, an analytic projective space, you'll take n+1 closed unit polydisks and glue these together subject to the usual formulas, much like the algeogeometric projective n space is a gluing of n+1 affine spaces. And in this context, for smooth connected spaces, global functions inject into their stalks, so you recover a good notion of unique analytic continuation. So for example, if your model space has a separation for the Grothendieck topology, then the sheaf condition, did I say? Yeah, I said it's a sheaf, very good. So the sheaf property would tell you that your global functions actually break apart into a product of these pieces, and therefore you would have a non-trivial idempotent. So in particular, if your coordinate ring was a domain, then there is no such thing, so there is no separation. So that would justify that for his limited class of coverings, thanks to the miracle of this theorem, your space has now restored a kind of notion of connectedness. Okay? Fantastic. Here's another example of a construction that was possible once he had this theory up and running. We can build, for example, analytifications of algebraic varieties, much like you do over the complex numbers. First, we have to build an affine space. So we take inclusions of the polydisk into the polydisk subject to scaling on the radius. You iterate this infinitely many times, so it's like an exhausting, growing family of polydisks. And then you declare that to be the analytic affine space. And there's an elegant universal property that Tate recognized that gave a small improvement in EGA1. And you can use that to show that this has the right universal property to deserve being called affine space, even if the construction didn't already convince you that it deserves that name. And great, once you have an affine space, then for any affine algebraic X, it's given by zeros in an affine space. You impose those on your analytic affine space, and now you've analytified any affine guy, and you can do similar things with projective spaces and other algebraic varieties. Wonderful. So now we can associate these new kinds of analytic spaces to algebraic varieties. And, but you have to be careful. So when working with this funny topology, there are some strange things that can happen. And so in this letter to Sayre, sort of Tate commented that some things that you might think are obvious are no longer obvious, and so even the master makes mistakes if he thinks a little bit too casually. And one of the sources of difficulties in working with these things is that you can't use pointwise arguments anymore. Okay, when you do analytic geometry over the complex numbers, you would take a point, you draw a little ball around it, you do something, you use local compactness. But here, the problem is that he manually declared the finite subcovers by definition. So somehow the theory is not sufficiently local in how it's set up, so you can't use pointwise arguments. Fortunately, at least for tasks related to coherent sheaves, these difficulties could be overcome. So for example, I mentioned on a previous slide that attached to every module, you had a corresponding coherent sheaf. So the converse result, that coherent sheaves necessarily come from modules, is much, much, much harder to prove than in the context of usual algebraic geometry. Kiel was able to overcome this, and then he was also able to prove a variety of other desirable theorems about coherent sheaves, despite the inability to use pointwise arguments. The proof of the GAGA theorem over the complex numbers also, in a few places, makes use of pointwise arguments, so you have to be a little more careful. But if you are, then you can adapt the proof of GAGA as well about the equivalence of coherent sheaves. And similarly, you can make rigid analytic constructions to which you apply the GAGA theorem and get interesting algebraic conclusions. So for example, in the 1990s, the Abiyankar conjecture on the structure of fundamental groups of affine curves and positive characteristic was solved by Raynaud and Harbader. And in order to solve the problem, they needed a technique to construct interesting finite étale covers, connected finite étale covers of algebraic curves. And they actually did this by using an analytic method and applying the GAGA theorem. Similarly, a lot of work with modular forms using p-adic analytic methods likewise as well uses the GAGA theorems. However, despite these successes in the coherent case, it's a huge problem. If you want to make a theory of étale cohomology in the non-Archimedean setting, the absence of pointwise methods is a real nightmare. Now, there was one early case where this could be avoided. So when Drinfeld did his work in the early 70s with his upper half spaces, which Jared Weinstein will talk about a bit in his talk later, he was able to make kind of ad hoc definitions for the cohomology groups that he specifically needed. But for later work that people wanted to do, you couldn't really invent the cohomology theory through ad hoc methods. You needed to do something else. So there were two approaches that both emerged in the early 1990s. So one by Berkovich. And so Berkovich has his Little Red Book. And in the introduction to his Little Red Book, he makes some historical comments. And in particular, he observes that Tate's approach gives you a good category of sheaves. But the problem is the lack of pointwise arguments prevents the direct application of geometrical intuition that you have over the complex numbers. So you might say that those rigid analytic spaces are in some sense regarded as spaces only in some conditional sense. You'd like to make something more robust that you can work with in a more pointwise way. So as I said, he and Huber both came up with quite different ways to do this, adding extra points to these rigid analytic spaces that allowed them to really do pointwise arguments. So in Berkovich's case, he added points corresponding, as I said before, the max spec, all points correspond to finite extensions. In Berkovich's case, he added points corresponding to certain non-algebraic extensions that were still fields with absolute values, so still corresponding to rank 1 guys. So for example, if you take the closed unit polydisk, then for each r from 0 to 1, you can take the sup norm on the closed polydisk, on the closed disk of radius r. This turns out to be multiplicative, so it extends to an absolute value on this, and you can take the completion. That gives you a point. And so these wind up being new points in the Berkovich space associated to this ring, so you even get a collection of points parameterized by a real number. And this will give rise to interesting path connectedness in this space, which is really bizarre when you first encounter it. On the other hand, Huber's approach, he went even, you might say, even more abstract. He added points corresponding to all kinds of higher rank valuations on all the fraction fields at all the primes of the ring. But amazingly, this exotic space that Huber constructed, its sheaf theory was identical to the sheaf theory that Grothendieck and Tate had developed. And in fact, the points of this space are exactly all the points of this category of sheaves. These two constructions were very useful beyond étale cohomology. Berkovich spaces get used in tropical geometry. Ducrot did some deep work on flatness in usual rigid analytic geometry by converting the problems to the Berkovich setting and using the nicer topological features here. Huber's approach with adic spaces was, of course, been used by Scholze and many others in the perfectoid setting. But I would like to first illustrate some more concrete examples of difficulties from the absence of pointwise arguments, or rather how these richer spaces solve some very concrete questions. So these Berkovich spaces, amazingly, even when the non-Archimedean field is highly not locally compact, like algebraically closed, the Berkovich spaces are locally compact and locally path-connected, and this allows you to do things that seem out of reach within Tate's original setting. For example, if I give you several functions in an affinoid algebra, and you consider their common zero locus, and take an open set around that, you would like to hope, if this space is somehow compact, that an open set around the zero locus should contain some tube on which the functions have absolute value at most some given epsilon. So that's what you would like to believe, that U should contain something of this type around the zero locus if epsilon is really small. And this can be shown by using Berkovich spaces, even though it's a statement in the Tate setting. I'm not aware of any direct proof of this using the Tate approach alone. So that's a very concrete question which you can solve by using these richer spaces. Another interesting example is when Kiel studied coherent sheaves, he proved theorems about proper maps and their push-forwards for coherent sheaves. But the definition of properness he gave was, in some sense, designed for his needs, but it's very hard to use. For example, until the year 2000, it wasn't known in general that a composition of proper maps was proper. What? Anyway, but this was eventually settled, and this was solved by, again, switching to the context of Berkovich spaces. In Huber's setting, he has points of a very different type than Berkovich, but it has other nice features, like it gives you a evaluative criterion for properness, which does not exist within the classical theory. So anyway, these extra points allow you to do some very concrete things, very useful. Okay, now let me tell you about another difficulty that arose in the attempts to grapple with the rigid analytic topology, which is that when you try to work locally on these spaces, the localized coordinate rings involve these Banach completions. So they're not commutative algebra completions, and so they're much harder to work with. So for example, I mentioned before this theorem of Kiel, that if I gave you a coherent sheaf on one of these affinoid spaces, locally it's easy to see that it has to come from a finitely generated module. But now you would like to deduce that globally this does. And the problem is, first of all, these things are some kind of Banach completions of A, so it's hard to convert structures over here to structures over here. But more difficult is the fact that you don't know in advance that the global sections are finitely generated. So it's very hard a priori to relate these to these given modules at the local level. Anyway, Kiel managed to overcome these, but as I said before, the proof of this is certainly much harder than in the algebraic setting. Another issue that would come up in gluing is that sometimes you have to work with tensor products, but they would be Banach-completed tensor products, much harder to use. So Tate wrote to Sayre about this in November of 1961. He said, the whole trouble is the hat on this completed tensor product. If only it weren't there, what he wanted to do, he could get using usual descent theory. But the hat makes it likely that one's talking through one's hat. Anyway, so it was hard to deal with this at first, okay? And the challenges of the completed tensor product, of course, show up in a lot of later issues as well. Okay, so I want to mention one last topic on this before we switch to formal geometry, which is the following. So in usual algebraic geometry, we often find it useful to pass to an algebraically closed base field, right? That's really convenient for a lot of technical and computational purposes. And so similarly, in developing rigid analytic geometry, Tate recognized right away that it's very useful to be able to have the theory not just over a perhaps discretely valued k, but over the completed algebraic closure, which is never discretely valued. And this is, when k is discretely valued, this thing is going to be infinitely ramified. In any event, the completed algebraic closure is never discretely valued. So you shouldn't limit the development only to the discretely valued case, because this will come back to haunt you later. And so he wrote to Sayre about this, that he'd solved some problems in the discretely valued case, and then it took him over a week, but he really worked hard. He wanted to get things in the general case. Okay. Similarly, and we'll come back to this in a moment, similarly with the adic spaces of Huber, well, these introduce higher rank valuations. So these are even further away from the discretely valued case. But those extra points are really useful. They make quasi-compactness. They give you other kinds of nice features. Now, interestingly, you recall at the beginning when I mentioned Grothendieck was getting super enthusiastic about this stuff, and he was saying, oh, we have to unify this with formal schemes and all these things. And in fact, in some sense, the adic spaces do exactly what Grothendieck wanted. They unify formal schemes and rigid analytic spaces. But strangely enough, Grothendieck hated higher rank valuations. Well, okay, at least in 1961. Maybe he came around later. So he wrote to Sayre in October of 61 complaining about this chapter in Bourbaki on general valuation rings. Like, get rid of it. Awful stuff. Composed valuations, all these, ordered groups. Horrifying. And yet, strangely enough, it's exactly these features that allow you to understand the topology of the adic spaces as well, which are exactly the ones that provide the unification that he was looking for. So, go figure. Okay. So that's non-archimedean geometry in a nutshell, and kind of some of the developments that came up along the way in turning this into a robust theory. But as I mentioned before, there are, and now we're going to discuss in a little more detail, there are these alternative approaches that people developed, and this is going to come back to the Tate curve as well, to how do you get your hands on the geometry and properties of these non-Archimedean rigid analytic spaces. So I want to start by coming back to the very beginning. If we consider an affinoid algebra over QP, a typical power series in here, the coefficients are going to 0. So in particular, eventually, they're all integral. But once they're integral, going to 0 becomes a purely commutative algebra property of being highly divisible by P in this ring. Okay? So in other words, your Tate algebra, there are only finitely many non-integral coefficients, so you can pull out the bounded denominator. What remains is purely integral, but in here, the convergence to 0 is a commutative algebra completion. All right, this hat is a p-adic completion in the sense of commutative algebra. So your Tate algebra is like a generic fiber over ZP of this commutative algebra completion. And then if you take quotients of this thing, then these are exactly the affine opens that show up in formal schemes of finite type over ZP. So when we say formal scheme, it's like a usual scheme, except instead of polynomials, we have power series, and the coefficients are going to 0 in the topology of the coefficient ring. Okay, well, if we take one of these guys, and then we algebraically invert P on it, Well, that just turns this back into this, which is equal to that. And so this kind of algebraic generic fiber of one of these guys is exactly a usual affinoid algebra. So this suggests the idea that we can interpret rigid analytic spaces as some kind of generic fiber for a formal scheme. More globally, if you take a formal scheme, it's covered by affine opens. For each of those, you invert P. This is we're working over ZP here. And then the gluing data on these turns into gluing data on these, and then you can create a space X that we might call script X, Gothic X ridge. We call it the rigid analytic generic fiber. Okay? And this has very good properties, and conversely, we might call the original formal scheme a kind of integral or formal model of the rigid analytic space. So this is a functor from formal schemes Gothic X to rigid analytic spaces. And this can be done not just over QP with ZP, but over any K with its valuation ring. And this relates well to the notion of analytification I was discussing before. If you start with an algebraic scheme over the valuation ring, you can now do two things. You can first take its completion with respect to the, like roughly a uniformizer of this, so doing the sort of things that are happening up here, and then take the rigid analytic fiber, generic fiber. Or you could take the algebraic generic fiber of this and then analytify that in the sense of what you do when you're analytifying for GAGA. The first one always sits inside the second one as an open subspace. For example, if you take affine n space over the origin, this completion process, rigid analytified, turns into a closed unit polydisk, whereas this side turns it into the big, much bigger affine space. On the other hand, in the proper setting, these winds up being the same. Okay, fantastic. So now I would like to use this viewpoint to come back to Grothendieck's complaint that Tate's construction had these brute formulas. And so let's see what's going on. So let's consider a discretely valued K, and we pick an elliptic curve with multiplicative reduction. Well, multiplicative reduction means that the Néron model over the valuation ring, that if we look at its identity component, the special fiber is a torus. Okay, we're going to assume the torus is split multiplicative reduction. We'll fix an isomorphism of the reduction with GM. That's unique up to sign. Now, the theory of tori over rings tells us that once you fix this, then all the higher reductions of the special fiber uniquely isomorph to GM, lifting this one over these thicker Artinian quotients of the valuation ring. Okay, great. These assemble, and these tell us that if we take the full completion of the relative identity component along the special fiber, we get exactly the formal completion of GM along its special fiber. Wonderful. Well, now you can turn this around. The E upper 0 sits inside E as an open, same thing at the completed level. So now inside here, we have a copy of the completed GM. Now we take rigid analytic generic fiber, so that's sitting here. This side is literally just this, which I think Dwork, I'm told, called the unit tire. And here, well, this guy, remember I mentioned before, the rigid analytic fiber of the formal completion sits as an open in the analytification of the algebraic generic fiber, but this script E sub k is just the original elliptic curve. Wonderful. So we now have the unit tire sitting inside as an open subgroup of this smooth of here, but it also sits as an open subgroup of this. Now this is connected. This is an open piece. So by uniqueness of analytic continuation, this is all completely canonical, no choices, well, except for that. And so this canonical map has at most one analytic extension to this, thanks to uniqueness of analytic continuation on smooth connected spaces. But that's exactly what Tate does, right? So Tate's brute formulas provide the explicit solution to this uniqueness problem. Right? So in that sense, they're an explicit incarnation of something that has kind of canonical meaning within the theory of Néron models. In fact, of course, Grothendieck did come to realize that this was the right way to think about it, because even in SGA 7, they sort of discussed this. And this whole circle, this approach to relating rigid analytic geometry, to come to non-archimedean uniformization was also extended to the non-discretely valued case in 1991. Okay, wonderful. So I now want to turn to a more systematic approach to this, because it's going to take us back to the Tate curve in a slightly different way. So we have this functor. Starting from a formal scheme, we have this rigid analytic generic fiber by inverting P on all of the coordinate rings. And as I said, this kind of motivated, or was one of the inspirations behind Grothendieck's dream of unifying Tate's rigid analytic spaces along with the theory of formal schemes. And in fact, Raynaud made this link much deeper. He proved a fantastic result that actually every reasonable quasi-compact rigid analytic space really does have such an integral model. And in fact, he even gave a uniqueness result up to some mild adjustment that's of a type that one would have expected. Even better, every map between two such things actually arises from a map between appropriately chosen integral models. Moreover, if this map was flat, this formal model map can also be arranged to be flat. And this is fantastic because what it opens up is the possibility of solving problems in rigid analytic geometry by converting them to problems in terms of these formal schemes. In other words, you reduce yourself to algebraic geometry over the valuation ring. So here's an example. So if you have a map of reasonable quasi-compact analytic spaces which is flat, you might wonder whether the image is open. Since in usual algebraic geometry, it's a fundamental fact that under reasonable assumptions, images of flat maps are open. But this question seems completely out of reach using usual rigid analytic techniques. But actually, if you pass through the formal models, it is instantly reduced to the issue in algebraic geometry, which was already known. Okay? So this is an example. So by using these integral structures, you can sometimes solve rigid analytic problems that were otherwise out of reach. Okay. So I want to now show you two very interesting constructions using the connection between formal schemes and rigid analytic spaces, which will show you that the world of rigid analytic spaces contains some really weird objects. Okay? So here's the idea. You start with something smooth, proper, connected over the residue field. And in that setting, you can sometimes use deformation theory to successively lift this over the various Artinian quotients of O, and eventually lift it to a smooth, proper formal scheme over O. And then the generic fiber of that is some smooth, connected, rigid analytic space, and it's also proper. And what I want to illustrate to you with two examples is how this process of starting from curious phenomena in characteristic P can give rise to some slightly disorienting phenomena in the rigid analytic setting over the fraction field of the valuation ring. So the first example is the following. In positive characteristic, the affine line has lots and lots of non-trivial connected finite étale covers. But a finite étale map can always be deformed, right? In deformation theory, there's no obstruction to lifting something étale. Well, this affine line can be lifted infinitesimally over the Artinian quotients of O. And so overall, you can lift this to the formal affine line over O. This lifts to a degree P connected finite étale cover. And then you can take the rigid analytic generic fiber. So in this way, we get non-trivial connected finite étale covers of the closed unit disk, which is really weird, right? If you've never seen that before. If your field has characteristic 0, that's a little bit disorienting because we think of the complex unit disk as being simply connected. But in characteristic 0, in the rigid analytic world, you have these p-power non-trivial connected finite étale covers. Okay, that's a geometric example. So now I want to give you a number theoretic example, which is going to allow us to apply the work of Tate in 3 different ways, or rather 3 different works of Tate. So Honda-Tate theory, which was mentioned in Poonin's talk, so this gives a classification of simple abelian varieties over finite fields in terms of VQ integers pi. And there's a formula for the dimension in terms of this Q integer, and that involves the P part of Tate's isogeny theorem for abelian varieties over finite fields. Okay, so I want to consider the following V P squared integer, P zeta 5, where P is a prime, and that's going to give rise to a 2-dimensional abelian surface where that's the V number over FP squared, and you can adjust this. If you're careful, you can adjust this to have Cm, complex multiplication, by z zeta 5. Hardly a surprise, because this is the Frobenius operator, and there's a zeta 5 sitting right there. Okay, now here's the interesting part. If you bring in deformation theory, the Serre-Tate deformation theorem that Laurie alluded to in his talk yesterday by studying the p-divisible group, you can show that this guy, together with this action, has a unique
z zeta 5 linear formal deformation to an abelian scheme over the corresponding quadratic unramified extension of QP. Okay? So starting from this abelian surface, we get this guy. So what? Well, here's the strange thing. If you take its generic fiber, it's an abelian surface. It's like a two-dimensional complex torus, but it's over a p-adic field. It has an action by a quartic number field. But if the prime is plus or minus 2 mod 5, then one can show that the action of this on the tangent space is not a CM type. And therefore, this is non-algebraic. Now, why is this interesting? Because over the complex numbers, any purely analytic complex torus with complex multiplication, the action of the CM field is always a CM type. It's unavoidable. But over p-adic fields, this can fail. So you can have these kind of analytic abelian varieties which have complex multiplication, but they're not algebraic, in contrast with the complex numbers where algebraicity is automatic and is, of course, very widely used. So anyway, there are some pretty strange rigid analytic spaces out there, even in characteristic 0. Okay, now let's come to the Tate curve and formal schemes. Okay, so as I mentioned before, we'll define the Tate curve to be the cubic defined by the Tate equation. But this guy living over the non-archimedean field, admittedly, it has a relation to the valuation ring because every quasi-compact, reasonable analytic space has a formal model. But we want to relate this to something that actually lives over z double brackets q. And the way that this is going to work is going to be, as we'll see, is going to be partly inspired by those renormalized expressions that I mentioned near the beginning of the talk. Okay, before I get into what Raynaud did to kind of bootstrap on Tate's work, I just want to mention 3 spectacular applications. So what we're going to discuss from what Raynaud did and using Tate's recipe to make the connection to the Tate cubic, Mumford in 1972 adapted this to higher genus curves and abelian varieties with totally degenerate reduction. And this was used by Deligne and Rappaport to develop a purely arithmetic theory of Q expansions and to understand the structure of modular curves over Z. And Faltings and Chai merged these 2 ideas to do similar things with abelian varieties in higher dimension. So what is it we want to do? So we're going to start with the projective cubic that I'll call boldface E over Z double brackets Q. This is a purely algeogeometric object. This is going to be given by the Tate equation. This has a discriminant, which is Q times a unit. And therefore, when you invert Q over this Laurent series ring over Z, these are finite tail Laurent series over Z, this is an elliptic curve because its discriminant is a unit. Okay, now what is the structure of the end torsion on this elliptic curve? So when I was a grad student, I was trying to learn these things. So there was a book I was reading which listed properties of the Tate curve, including the structure of this end torsion, which I'll discuss in a moment. But the only definition that was given was this cubic. And I was completely mystified as to how can you stare at that cubic equation and figure out the structure of this end torsion as a group scheme over this ring. So I was completely puzzled, so I emailed Tate. Yeah, so he didn't see a way either to get this out of the cubic. So the way that we're going to get this, as we'll see shortly, is through using Raynaud's approach through formal schemes, and what Tate told me was that was also the only way he knew how to do it as well. Okay? So, all right, so how do we get our hands on this thing through another approach than just writing down an equation? So let me first give the motivation for how you would think about the end torsion. If we take the uniformization at the level of the rational points and you look at the end torsion, you can just compute it explicitly. You take an nth root of this guy and you take an nth root of unity. And this thing, as a Galois module, has a quotient that's z mod n, generated by this mod that, and has a subgroup consisting of the roots of unity coming from here. Okay? So this is some kind of Kummer extension, exact sequence, and it's classified by this unit in the base field. Well, you could then ask, is the end torsion in the Tate curve as a group scheme an extension of z mod n by mu n as group schemes, and is it also classified using Kummer theory by this unit? And the answer will be yes, but it involves Raynaud's formal schemes. So let's see how this goes. So we start with the uniformization, and we think about this K star as being exhausted by annuli. So you draw an annulus of radius between 1 and absolute q, and you expand it outwards and inwards by using multiplication by powers of q. So you imagine a punctured plane being tiled by these successive nested annuli. So these are the nested annuli, and each one can be converted into the basic annulus by using a rescaled variable, where this guy here is simply this coordinate. These are all the same, no matter what I is. I'm just keeping track of an indexing on the variable to remember where it came from, okay? And these guys, so these are these annuli, and the way that they relate to each other in the punctured plane is the locus where absolute x is 1, absolute xi is 1, is like the outer edge, and the locus where the corresponding y variable has absolute value 1 is the inner edge. So the outer edge of the first guy is the inner edge of the second guy. So this is this locus here, and these guys on the overlap are related through this relation. Multiplication by the parameter q0 carries one annulus into the next annulus, and it respects the coordinatization by these x's and y's. Well, these descriptions here don't involve any division by p, so you can do this formally. We work over z double brackets q. We introduce the relation. We have these formal annuli. They have these open formal subschemes. And we're going to glue these to each other using the same relation that we saw here. Since we're working integrally, we have to keep track of a little bit more information. But the point is, this gluing of formal annuli can be done just in analogy with this, and you get this enormous thing. Okay? Topologically, it's a chain of p1s whose singularities at the overlaps have been thickened up to something like this. The point is that not only do you get this enormous gluing, but the q multiplication that moved one annulus to the next can be turned into a free action of z on this, which carries one formal annulus to the next by simply doing a shift of the formal coordinates on each piece. This thing is enormous, but the free z action, you can take a quotient, and that collapses the non-quasi-compactness into quasi-compactness, even separatedness, and even properness. So this is Raynaud's construction of some curious proper formal scheme. And this guy, we'll see, by using Tate's renormalized formulas, will be related exactly to the original cubic. From a purely abstract point of view, this funny quotient is a formal relative curve. It has an explicit section through its smooth locus. And mod q, which means you collapse everything to working over z, the inverse ideal sheaf of this will be relatively ample. And therefore, by using Grothendieck's GAGA theorem for formal schemes, this abstract formal scheme has to come from a unique algebraic proper curve over here. The question is, we don't know what it is. But even before you know what it is, before you figure it out, general theory will allow you to infer that inverting q on this gives you an elliptic curve, and that its n torsion must be a Kummer extension of z mod n by mu n, having exactly the desired type you would like. So this can all be inferred from the abstract approach to the formal scheme, but the question is, what is this E? Okay. So now this is where the algeogeometric meaning of Tate's series will come to the rescue. So these are going to give us an isomorphism of this abstract Gothic E onto the formal completion of the Tate curve, and thereby show that this abstract algebrization is the original Tate cubic. So what's the relation? Well, those x's and y's, they can make sense mod q to the n, and they become these polynomial expressions with mild poles. These are the polar parts of the x and the y. And if we look at these mod powers of q, you can interpret them on rational functions of the reduced formal annuli. And as such, each formal annulus can be mapped to P2 by imitating the Weierstrass mapping using the corresponding x and y. You have to, of course, adjust for the poles in the usual way. And these maps wind up agreeing on the overlaps of this gluing. Ultimately, it comes down to certain identities for these modified functions, which come back to these classical formulas for invariance under Q multiplication. But the upshot is that because these agree on the overlaps, they give you a map from the mod Q to the n reduction of this massive gluing into P2 over your quotient. But everything is compatible with n, so it gives you a map from the full formal scheme to the completed P2. On the other hand, this is constructed from the x and the y. They satisfy the Tate cubic. and therefore this map lands inside the locus for the Tate cubic. And you can check by working mod q to the n that this mapping is invariant, and therefore you get a map from here to here. And in view of time, I'll just say that you can show that this map is an isomorphism by reducing mod q, and then you're over z, and then you check over the residue fields, and ultimately what you have to show is that a very concrete map at the level of the singularities is an isomorphism. It's just those polar parts, and this is just some calculation on the tangent spaces. Okay, anyway, the upshot is that the original Tate formulas, when you renormalize them and get rid of the negative exponents and make sure it makes sense to do reduction mod powers of q, they exactly witness the realization of the Tate cubic as giving the algebraization of the abstract formal scheme. Okay, this is the last slide. So I just want to end with one final comment, which is, so we've discussed the discretely valued case, the non-discretely valued case, and how it's very useful for some problems to pass up to the completed algebraic closure. So now I want to go in reverse. So I just want to point out the following cute thing, which is, whoops, sorry. So if I give you a smooth proper analytic space, suppose you know a result when you're over local fields. And then you can ask, is that enough to infer things in the general case, such as over CP? So this was a suggestion that Scholze made, which is the following. If you're trying to prove some result in a general context, and it makes sense in families, then if you want to prove it for something over a possibly infinitely ramified field, if you could somehow realize your y as a fiber in the base change to k over some point of an arithmetic family, in other words, you start with a y over k, you're seeking some smooth proper family over a QP aphanoid base, so that when you base change this to k, some fiber over a k point gives you original y. If you could do that, then you could hope to take a result known in the arithmetic setting and deduce it in general. And so a priori, this seems like a difficult problem because analytic space is described using power series that have infinitely many coefficients, but it turns out that if you bring in techniques from formal schemes and deformation theory, that you can actually answer this in the affirmative. So you can not only use completed algebraic closures to solve problems over discretely valued fields, but sometimes you can use results in sufficient generality over discretely valued fields to deduce things in the infinitely ramified case as well. All right, so I'll stop there.